Uh, Bismillahirrahmanirrahim. Uh, Today we are going to start chapter 4, that is about the bending. Till now we have studied chapter 2 and chapter 3. In chapter 2 we have studied that if we have if we have a beam like this one and an axial load P is applied on it, that may be a compressive load or that may be a tensile load. So if I take the cross section of this, so this P will be causing an internal force, that will be the reactionary force against this action P, that will be equals to sigma, right? And sigma is equals to P by A, right? So sigma is force per unit area or load per unit area, right? Then what we studied? We studied epsilon. Epsilon was the strain, and that was either equals to sigma over E, that was the Hooke's law, or epsilon was equals to del over L. Del was the extension and L was the original length. So from there we calculated the del. Del was the extension and that was PL over AE. P was the load, this load. L was the length of the beam. A was the cross-sectional area. And E was the Young's modulus or the modulus of elasticity for that particular material. Right? So load is given to you, length is fixed, area cross-sectional area is fixed, and E is the material property. From there we can calculate del, right? So this was the chapter 2, which was all about in which an axial load, which may be a compressive or a tensile load. So we calculate different values of normal stress, normal strain epsilon, and delta, that was the extension of that particular material, right? In chapter 2, in chapter 3, what we discussed? We discussed that we had a rod. We had the rod like this one, and if this was X, Y, and Z direction, and a particular type of moment is applied along X-axis, that particular type of moment causes the torsion, and that is called the torque, right? Rest of the moments in the direction of Y and direction of Z cause the bending, while the torque that is along the x-axis causes the rotational effect, right? So what we did, we calculated the tau, we calculated gamma, and we calculated that was phi, right? Torque was Tc over J. T was the torque, C was the distance, that was the maximum, tau max, it is for the tau max value, And otherwise, if it is not at C, means outermost periphery of the rod, so we can go for the Y or the rho, right? And J was the polar moment of inertia. Obviously, by having this value, we can go for the tau max or value of torsion at any particular value of rho, that is the distance from that particular point to the center one. Gamma, that was the torsional strain, that was equals to tau over G. G was the modulus of elasticity, right? And when this movement was around x-axis, so a torque is being applied on the rod, and that torque is causing the change, angular change in that particular rod. That was equals to phi, and that was equals to TL over GJ. T was again torque, L was the length of this particular section from here to here, G was the modulus of elasticity, and J was the polar moment of inertia, right? What we did was, we know how to calculate the J for a solid rod, for a hollow rod. G was the material property, T was the torque that can be calculated or that may be given to you, and the length is known. So from there you can calculate phi, and phi was the angular distortion or angular deformation in that particular one, right? So if we go for a demonstration for this one, so this was the rod, right? And we were applying the torque on it, and this torque was along the z-axis. My thumbs are in the direction of, along the direction of the x-axis, and I am giving a particular torque on it, and it is being distorted. Angular distortion is there, and whenever angular distortion is there, so we have to go for the torsion and torsional strains, and angular deformation, that was equal to phi, and that expression has already been given to you, right? Fine. So these are the two chapters, review of these two chapters. Now chapter 4 deals with the bending, right? This was the one torque that was being applied in the direction or the along axis or the y-axis, x-axis, sorry, and the rest of the two moments that are being applied in x, in y and z direction, that cause the bending, right? Like this is a square rod I have, right? So initially chapter 3 deals with this one, right? This one, angular deformation, and my thumbs are in this direction, right? So it is in the x direction. This is my y direction, and this is my z direction, out of plane, right? Now I am applying a moment in it. It is causing bending. And where are my thumbs? Thumbs are towards me, right? In this direction, right? It is towards you, or it is towards me now. That is the z-axis. So mz is causing, moment about z-axis is causing this beam to bend, right? And likewise, if I do this in a way, it will be my again causing the bending. So this is because my thumbs are in y direction, upward direction, right? This is my, this is mz, and this is mx, that is called torque, and we deal with it in chapter 4, chapter 3, sorry, right? Fine. So so in this particular chapter, we will be dealing with mz. Mz means the moment about z-axis, and it will cause a particular bending in it, this way, right? And what is the plane of bending in this particular case? It is xy, right? So moment is in the z direction. Plane of bending is xy and moment is in the z direction. And in this particular case, moment is about the y-axis and plane of bending is x and z-axis, right? So what is happening now? When I am applying the bending about z-axis or the moment about z-axis, bending is being caused. And when bending is there, so inner surface is being compressed and outer surface is being stretched, right? So this is the compression area and this is the bottom is basically the tensile area. And we know from chapter 2 that whenever we have that variation from top to bottom, from compression to tensile, so we are moving from negative normal strain to positive normal strain, right? Compression is always positive, negative, and tensile or the stretching is always positive one, right? So there should be some, so you are moving from here to here, negative to positive, so there should be some surface along this length where you will come across come across the stresses where its value will be zero. Obviously, when you will be moving from maximum to minimum, from negative to positive, there will be some surface where that particular stresses will be zero. That surface is called neutral surface, right? This along the length, that is called neutral surface. Whereas when I'll see this surface over here, almost in the center, it may vary, but because this is the uniform cross-sectional area, so it will be around this axis. This is called neutral axis, right? This is neutral surface and this is neutral axis, right? Fine. And this is basically the one which I'll show you in the shares, slide shares as well. Right. Okay, we must go for the slide share now. Fine, I'll stop the video now, right, for a moment. Okay, fine. Now, now this is basically the bend surface, right? And this is called y-axis, neutral surface. If I take this cross section in this direction, so this axis will be called neutral axis. This is under compression, so negative, and this is under tension, so positive. So moving from negative to positive, there will be some surface like neutral surface where this normal stresses will be zero. See, right? So there is no distortion, no angular distortion is involved in this case. You are applying a bending in this direction and in this direction, that is mz along z axis, because this is x, this is y, and this is z, right? So you are applying the moment about z-axis and that is causing the bending. Since there is no angular deformation, so we will not deal with the torsion. We will deal with the normal stresses, normal stresses, right? So normal stresses will be there, normal strains will be there, because we are no more dealing with any angular deformation, right? Whenever there is compression, whenever there is tension, there is change in length, not change in the angular or any sort of angular deformation. So whenever there is change in length, so we always used to call it normal strain. So in this particular chapter, we will be always dealing with the normal stresses. Normal stresses mean you will be dealing with sigmas, you will dealing with the epsilons, and blah blah blah. So it is almost the regular chapter like the chapter 2, which deals with the sigma. But the difference, what is the difference between them? In that particular case, in that particular chapter 2, what we assumed was that what we assumed was that the stresses, the normal stresses across this surface are the average one, if you remember, right? But in this particular, it is not the case, right? It will not. It is varying from top to bottom in a different fashion. But normal stress sigma and normal stress strains epsilon was distributed equally on this surface, and we took the average of these surfaces. But in this chapter 4, we will be dealing altogether a different scenario. Although we will be dealing with sigmas at epsilon, but they will not be equal across the surface. They will be different, and we will see how it varies from this neutral surface. This is what we know now, that from this expression, from this picture, we know that at neutral surfaces, normal stresses will be zero, resultingly strains will be zero, or normal strain will be zero, resultingly normal stresses will be zero. But above that and below that, it will be varying, and that will depend again, like the torsion we did, that it will depend upon some distance from the center, and as we go on the outer surface, it will keep on increasing, and as we keep on uh, coming towards the neutral axis or the center of the beam, it will keep on decreasing, and it can vary from minimum to minus to positive mean, from from compressive loads to the bottom side of the positive loads, right? So this is what all about this chapter is, that we deal with primarily with the normal sigmas there. uh, so we in this chapter we will be primarily dealing with the sigmas, epsilons, and uh, and del over there, right? So these are the same nomenclature that we used in chapter 2, right? So now we will come on the slide part of that one. So now we will going to start the regular lecture from the presentation. Presentation has already been uh, shared with you guys, right? So you can go for it accordingly, and it has been shared with you, right? And it is in the presentation mode, and I'll stop the video so that it remains, right? So pure banding. So in this particular chapter, we will be dealing with the pure banding, right? So we have this M and M dash, as we have already demonstrated in the video as well, that this is a prismatic beam. Prismatic beam is a beam which has the uniform cross sectional area across the length. If there is variation, if there is any sort of variation, if there is any sort of variation in the cross-sectional area, that is no more called the prismatic beam. So in this particular chapter, we will be dealing with the prismatic one, right? So in the preceding chapter, you studied that how to determine the stresses in the prismatic member subject to the axial loads or the twisting couples, like in chapter 2 and chapter 3, right? In this particular chapter, we will be dealing with the bending, and how the bending is being caused. That is being caused because moments about y-axis and z-axis cause the pure bending. This is the chapter with the pure bending. In next chapter somewhere we will deal with the bending shear as well. So that is the scope of the chapter 5, not in this period. In this, we will assume that there is pure bending, no shear stress involved, any sort of shear stress involved, although shear stress is being involved whenever there is bending. But for the chapter 4, assumption is no shear stress is over there, no shear force is there, right? So we will be taking the case of pure bending, right? So pure bending, what is pure bending? This is the weightlifter who is lifting a certain amount of weight, right? And you can see that what he is doing, he is taking 80 pounds on either side of that, and to to lift it, the the opposite equal and opposite force is being applied by these hands, right? Sorry. Right, so these are the forces which are being caused by these two hands, and these are the forces which are coming from the so if I take the cross section about this axis, so there will be pure bending moments like this one and this one. And moment, we know it is 80 multiplied by 12, and 80 multiplied by 12, it is 960 pound per inch, sorry, pound inch for that one, right? So in this particular section CD, there will be a pure bending, although there will be some shear force as well, but we will ignore that, we will deal with it in the chapter. So equal and opposite forces are being applied by the hands, which is RC and RD, which is equivalent in amount with the 80 with the weight on the either side of the hands, right? So another case is eccentric loading. Again, chapter 1, we deal with the we have already been we have already been dealing with this one, right? So let's pause here for a second, and then I'll start. Uh, let's pause for here, and I'll restart the video to keep its size smaller, right? So I'll end meeting.